Hello dear students, and welcome back to our class for this week. Today I'll be discussing on linear Diophantine equation, which I had mentioned in the earlier lecture. And if you remember, a Diophantine equation is an equation in one or more unknowns that is to be solved in integers. Okay, so the name honors the mathematician Diophantus, who initiated the study of such equations. Okay, so any equation which is to be solved in integers, okay, we need the integer solution. Such an equation is called a Diophantine equation. So as a particular case, we will study the linear Diophantine equation in two unknowns. Okay, that is ax plus by equal to c. Okay, say x plus twice y equal to 7, twice x plus 8y equal to 93. Okay, like that. So this type of equations we will study. So here a, b and c, they are all integers, okay, and a and b cannot be simultaneously 0. Okay, thus we are required to find all integers x and y which satisfy ax plus by equal to c. Okay, so a linear Diophantine equation can have many solutions. For example, let us see one simple example. Twice x plus 4y equal to 12, okay, has many solutions. X equal to 2, y equal to 2. See, if we put x equal to 2 here, 2 into 2 is 4, and y equal to 2, 4 into 2 is 8, 8 plus 4 is 12. Okay, so this is a solution. The first one is a solution. What about the second one? X equal to minus 2, so it's minus 4, plus y equal to 4, so it's 4 into 4, 16, 16 minus 4 is 12. So second one is also a solution. The third one, x equal to 6, y equal to 0, this is also a solution. Okay, so in fact we will see in this lecture itself, there are infinitely many solutions for this equation. Okay, however, a linear Diophantine equation may also possess no solution. Okay, so it may also happen that there are no integers which satisfy a particular Diophantine equation. For example, twice x plus 4y equal to 3. Okay, this equation does not have any integer solutions. Okay, so how we can justify? In this case, it's quite simple to justify. If you observe, the left hand side is a even integer, right? Because x and y are integers. Left side is twice x plus 4y, which is an even integer, but the right side is a odd integer. So even integer and odd integer cannot be equal. So this system, this linear equation doesn't have any integer solution. Okay, so there are several cases. So let us see how we can find out a general solution of any given Diophantine equation. So for this, we have this theorem, which is not very difficult. It's quite simple to prove. And given that already you have done GCD and properties of GCD, greatest common divisor, it will be quite easy for you to understand the solution, the proof. Okay. So the linear Diophantine equation ax plus by equal to c has a solution if and only if d divides c. Okay. What is d? D is the GCD of a and b. Further, if x0, y0 is any particular solution of this equation, then all other solutions are given by x0 equal to x equal to x0 plus b by d into t, y equal to y0 minus b by d into t. Oh, sorry, I made a mistake here. Y equal to y0 by y0 plus a by d into t. Okay, this will be a. Please correct it. This is your a by d into t. Okay, please make this correction. Yeah. So let us see where t is any integer. So we have infinitely many solutions. Once we are able to find out a particular solution, then we will actually have infinitely many solutions. Okay. So let us see the first part. The first part is the criterion for existence of solution. Okay. Suppose that ax plus by equal to c has integer solution. Now say x0 and y0. Then ax0 plus by0 is c. Okay, and if d is the GCD, then we have d divides a and d divides b. Right, greatest common divisor of two integers divides both the integers. It's a common divisor. Okay, so we have d divides a and d divides b, where d is the GCD of a and b. Next, we have seen one very important property of divisibility, which we have already used so many times in many equations, many problems. Okay, so this is the particular property of divisibility. if D divides A and D divides B, then D also divides their linear combination. Okay, so D divides A, D divides B, so this will imply D divides AX naught plus BY naught. But what is AX naught plus BY naught? We have seen that it's equal to C. So D divides C. So if the equation has a solution, then D has to divide C. Now there is another part, that if D divides C, then also we can find out a solution. Okay, so the other part, the converse part. So conversely, so we start with this part. Conversely, let D divides C. Then since D is the GCD of A and B, so there exist integers R and S such that AR plus BS equal to D. Okay, so this problem was also done in your course. If D is the GCD of two integers A and B, then we can find out integers X and Y which satisfies AX plus BY equal to D. Okay, so this is what we have written. Okay, so instead of X and Y, I have just written R and S. So from here, what is our conclusion? Since D divides C, so C can be written as D into some integer T. Okay, for some integer T. So multiplying 1 by T, if we multiply 1 by T, what we will get? ART plus BST equal to DT. Okay, so A multiplied with RT plus B multiplied with ST is equal to C. That means what? RT and ST are solutions of AX plus BY equal to C, right? Because RT and ST, they satisfy this equation, A multiplied with RT plus B multiplied with ST equal to C, right? So what we have seen? We have seen that if D divides C, then also we can extract one solution of that given equation. So it's a if and only if condition, that is AX plus BY equal to C has integer solutions if and only if. Okay, this is the notation for writing if and only if. Okay, what does it mean? So it means there are two statements here, two implications actually, two implications here. AX plus BY equal to C has solution implies that D divides C. Okay, and the other way, D divides C implies that AX plus BY equal to C has integer solutions. Okay, so the first part of the theorem is over. Okay, the second part, if X naught Y naught is a solution of AX plus BY equal to C, let X bar Y bar be any other solution. Okay, so what is our aim? Our aim is to express any other solution in terms of a particular solution. Okay, so if X naught Y naught is a solution, then AX naught plus BY naught is C, right? And AX bar plus BY bar is also C. So if we compare these two, we can write AX naught plus BY naught equal to AX bar plus BY bar. Okay, so just change the sides, A into X naught minus X bar equal to B into Y naught minus Y bar. Okay, Y bar minus Y naught. Now D is the GCD of AB, so there exist integers R and S with GCD of RS equal to 1, such that A can be written as D into R and B can be written as D into S. Okay, this is also property of GCD. Okay, from any number, given any two numbers, okay, we can write each number as GCD multiplied with some number, and the GCD of the resulting two numbers will be 1. Okay, so here I have given one star mark to say that we have assumed that A and B are both non-zero. Okay, so R and S are also non-zero. Okay, we will do the zero case later. So here we are assuming that A and B are non-zero, right? So from this equation 2, what you get? dr multiplied with X naught minus X bar equal to ds multiplied with Y bar minus Y naught. So since A and B are non-zero, so this greatest common divisor is non-zero, right? So we can divide both sides by D, so we are left with R into this equal to S into this. Okay, so since R and S are non-zero, so what we can see? We can see from 3 that R divides this quantity. Okay, R divides the right hand side. Okay, but there is no common factor between S and R, right? There is no common factor between S and R. That means R has to divide the other factor. Okay, R divides S multiplied with this, but there is no common factor between R and S. That means what? R has to divide the other factor. So R divides Y bar minus Y naught. Okay, so y bar minus y naught can be written as r into q for some integer q. Okay, so y bar can be written as y naught plus rq. Okay, and if we put that value here, y bar minus y naught can be written as rq. So we put this value here. Since r is non-zero, we divide by r, and we can write x bar as x naught minus sq. Okay, so thus any solution x bar y bar of the given equation is written as x bar equal to x naught minus sq. What is s? S is b by d, right? And y bar is y naught plus a by d into q. Okay, right? Y bar was y naught plus rq. Okay, what is r? R is a by d. Okay, so this is equivalent to writing, so where q is any integer. Okay, q is any integer, so this is equivalent to writing x bar equal to x naught plus b by d into t. Okay, and y bar equal to y naught minus b by d into t, because if q is an integer, minus q is also an integer. Okay, so you can, these two forms of writing the general solutions are equivalent. Okay, so you can either use this form of writing or use this form of writing, no problem. Okay, but we cannot mix up. You cannot write x bar equal to x naught plus b by d into t and y bar equal to y naught plus a by d into t. Okay, that cannot be done. You cannot mix up these two. Okay, these two cannot be mixed up, right? We have to either stick to this part, or we have to stick to this other part. Okay, right? So now let us see the case if one of them is 0. If a is 0 but b is non-zero, then ax plus by equal to c has a solution if and only if GCD of ab divides c. That is same as the earlier one, that is b mod b, but GCD of a and b when a is 0 is modulus of b, mod b divides c. So all solutions are given by x can be any integer and y has to be only one integer, that is c divided by b. Okay, right? Since a is 0, this equation actually becomes by equal to c. So y can be written as c by b, and x can be any integer. Okay, right? So this is a particular case. So yeah, we have seen that if the linear Diophantine equation has one solution, then it has infinitely many solutions. Okay, so let us see one problem. Solve the linear Diophantine equation twice x plus 3y equal to 5. Okay, so we have GCD of 2, 3 is 1 and 1 divides 5. Okay, so this equation will have a solution. Okay, so one solution is given by x naught equal to minus 5, y naught equal to 5. This is by observation. If you put x equal to minus 5, here you will get minus 10, and here if you put y equal to 5, you will get 15. 15 minus 10 is 5. So by observation we get one solution. So by the above theorem, all other solutions will be given by x equal to x naught plus b by d into t, y equal to y naught minus a by d into t. Okay, so x can be written as minus 5 plus 3t, and y can be written as 5 minus 2t. Okay, where t is any integer. You take t equal to 0, you will get one solution. Take t equal to 1, you will get another solution. Take t equal to minus 1, you will get another solution. Okay, many solutions are there. So for every integer t, there is a solution. Okay, so here we get x equal to minus 5 plus 3. So here I have taken t equal to 1. So y equal to x equal to minus 2, y equal to 3 is a solution. Similarly, if I take t equal to 2, then x equal to 1, y equal to 1 is also a solution. Okay, so the general solution can also be written in terms of this 1 plus 3t and 1 minus 2t. Okay, this will also serve as a general solution. Okay, even we can write minus 2 plus 3t and y equal to 3 minus 2t. Okay, so many ways of writing the general solutions, or ultimately we will get the same set of solutions. Okay, so here in this problem that we have done, we have got a solution just by inspection. Okay, or trial and error, but in every case this may not be possible. Okay, in fact it's very hard. So in most problems it is difficult to guess a solution just by observation. So in such cases what we can do, we can make use of the Euclidean algorithm. So this was also discussed, Euclidean algorithm to find integers x naught and y naught such that ax naught plus by naught equal to t. Okay, Then what we do, we can multiply both sides by c by d to obtain the solution of ax plus by equal to c. Okay, so let us see how we can do that. Solve the Diophantine equation 56x plus 72y equal to 40. So it's very difficult to find out which values of x and y satisfy this by trial and error. It may happen that you may get in the first trial itself. Okay, it may happen that you may not get in the 100th trial also. Okay, so there is no surety. If you get in the first trial itself, no need to go for the Euclidean algorithm. Okay, you just write the general solution. Okay, but yeah, so I request you to go with the Euclidean algorithm so that you can understand the process nicely. Okay, right. Even if in exams you have these equations, if you are asked to solve these equations, you go for the Euclidean algorithm and derive it nicely. Okay, derive the solution nicely. So GCD of 5672 is 8. Okay, and 8 divides 40. Right. So the equation has solutions. By our theorem, equation will have solutions. So we use the Euclidean algorithm to find integers x and y such that 56x plus 72y equal to 8. Okay, so what was the process? The process was you start with the larger number. So 72 equal to 56 into 1 plus 16. Okay, and then take this divisor in the earlier step and remainder in the earlier step. Okay, so 56 can be written as 16 into 3 plus 8. Okay, and then again 16 can be written as 8 into 2. Okay, so then you start the back substitution. So start from this second equation. 8 can be written as 56 minus or 56 plus 16 into minus 3. Okay, and then 8 can be written as, instead of this 16, I'll use 72 minus 56 from the first equation. Okay, so this is how ultimately we are trying to write 8 as a linear combination of 56 and 72. Okay, so that is why we will substitute only for this 16. Okay, only for this 16 from here, from the first equation. So 8 can be written as 56 minus 3 into 72 minus 56. Okay, so 3 minus plus 3 into 56, and here you have 156. So ultimately you will get 4 into 56 plus minus 3 into 72. Okay, so thus 56 into 4 plus 72 into minus 3 is 8. Okay, but what do I need? I need 40 in the RHS. So how can I get 40? We have to multiply both sides by 5. Okay, so 56 into 20 plus 72 into minus 15 equal to 40. So we have got a solution. This is a particular solution, 20 comma minus 15. X equal to 20, x not equal to 20, y not equal to minus 15 is a solution. Okay, all other solutions are given by x equal to x naught plus b by d into t and y equal to y naught minus a by d into t. Okay, so it's 20 plus 90 and y equal to minus 15 minus 70, where t belongs to integers. Okay, so these are the solutions, all possible solutions, right? And so let us see another such problem. Determine all positive integer solutions of this equation. 18x plus 5y equal to 48. Okay, so we have GCD of 18 and 5 is 1 and 1 divides 48. So the equation has a solution. So we'll use the Euclidean algorithm again. 18 can be written as 5 into 3 plus 3. Okay, and then 5 can be written as 3 into 1 plus 2. Okay, and then 3 can be written as 2 into 1 plus 1. So we start from the last equation here. So 1 can be written as 3 minus 2 into 1. Next, what we do, we are replacing this 2. Okay, we are replacing this 2 from the second equation. Okay, so from the second equation you will see we get 2 equal to 5 minus 3 into 1. Okay, so it's ultimately 2 into 3 minus 5. Now what we are doing, we are replacing this 3. Okay, we are replacing this 3 from here. Okay, from here we are replacing the 3. Okay, from this position we are replacing 3 at this position. Okay, right? So this is 1 equal to 2 into 3 minus 5. So 1 equal to 2 into, instead of 3 we can write 18 minus 5 into 3. Okay, so it's ultimately 18 into 2 plus 5 into minus 7. Okay, so this is the solution. Okay, so this is the solution for 18x plus 5y equal to 1. Okay, but I don't need 1 in the right hand side, I need 48. So what we do, we just multiply both sides by 48. So you will get 18 into 96 plus 5 into minus 336 equal to 48. Okay, so now from here you can easily understand that it's the trial and error method doesn't work. Okay, it's very difficult to get this by trial. X is 96 and y is minus 336, it will satisfy this. Okay, so you have to know what is the Euclidean algorithm. Okay, so x naught is 96 and y naught is minus 336 is a solution. Okay, all other solutions are given by what? 96 plus this 5 by 1 into t minus 336 minus 18 by 1 into t. Okay, so for positive integer solutions, what we should have, we should find the values of t for which this is greater than 0 and this is greater than 0. Okay, both of them should be greater than 0. Okay, so t is greater than minus 96 by 5 and t is less than minus 336 by 5 by 18. 96 by 5 is actually 19 and 1/5. Okay, and 336 by 18 is 18 12 by 18. Okay, or 18 2 by 3, right? So we have t lies between minus 19 point something, okay, to minus 18 point something. That means but t is an integer, so what is the integer which lies between these two values? Only minus 19. Okay, minus 18 also doesn't lie between these two. I had written earlier but I had cut here. Minus 18 is actually greater than minus 18 point something. Okay, so only one positive integer solution exists corresponding to t equal to minus 19. So what is that solution? X equal to 1 and y equal to 6. This is the solution. Okay, so from the 25th problem from the last lecture, we had one problem where each pen costs 11 rupees, pencil costs 13 rupees. To find out the number of ways in which we can buy pen and pencil, so that the exact value is exact cost is 1000. This was the problem. So this problem also we can solve using the Diophantine equation method. Okay, I had mentioned that earlier in the last video. So here you see GCD of 11 and 13 is 1. Okay, so our problem actually reduces to finding integer solutions for this, positive integer solutions for this. Okay, positive or non-negative integer solutions for this. Okay, so this is a Diophantine equation. GCD of 11 and 13 is 1, so and 1 divides 1000. So we use Euclidean algorithm to find out the expression. So 13 can be written as 11 into 1 plus 2, 11 can be written as 2 into 5 plus 1. So from here we start back substitution. 1 can be written as 11 minus 2 into 5. Then in place of 2 we substitute 13 minus 11. Okay, so ultimately we will get 11 into 6 plus 13 into minus 5 is 1. Okay, so you multiply both sides by 1000, we get 11 into 6000 plus 13 into minus 5000 is 1000. Okay, so any solution is given by this x naught plus b by d into t. Okay, and y naught minus a by d into t. Okay, this is any given solution. So for non-negative solutions, this x should be greater than or equal to 0 and y should be greater than or equal to 0. That means t should be greater than or equal to minus 6000 by 13 and t should be less than or equal to minus 5000 by 11. So if you just convert it into a mixed fraction, you will see it's 461 7 by 13 and this one is 454 6 by 11. Okay, so ultimately, so it's t is an integer which lies between minus 461 point something to minus 454 point something. Okay, so that means t takes the values minus 461, minus 460, minus 459, minus 458, minus 457, minus 456 and minus 455. Okay, it doesn't take the value minus 454 because 454 minus 454 is greater than, it lies somewhere here. Okay, it's greater than minus 54 point something, right? So there are 7 values of t which satisfy this. Okay, so in the earlier video also we had obtained that there are 7 possibilities. Okay, so this is another way of doing, right, using Diophantine equation. So I'll post another video probably tomorrow for this week with some problems. Okay, so here I have just discussed the theory. I'll take up some problems in the next video tomorrow. Okay, thank you.